Welcome to the lecture series of Basic Electrical Engineering. The subject code is ECE 101. The topic of this video is transient response of RL and RC circuit. In this video, we will discuss the important equations of RL and RC network and how we represent them for solving the numericals. We discuss all these things one by one. First of all, we will discuss transient response of RL circuit. This circuit is shown in which we are having a voltage source V. This is the negative sign and the positive sign, and here we are having the resistance and inductance connected in series, and we are having a key which is connecting at one time it is connecting with 1 and another time it is connecting with the switch 2. So we are discussing this circuit provides us two circuits, one when it is connecting with 1 and second when it is connecting with this 2. So this circuit shows when we consider that initially this is connecting with the switch 2. So the first case is when switch moves from 2 to 1. When it moves to 1, it means that it is connecting with 1 and the circuit will become this, in which we are having a voltage source, let's say it is 15 volt, and a resistance of 1 ohm and a inductance of 1 Henry. So this is the case when we are having the key connecting from 2 to 1. Second circuit shows that when we are having this switch 2 moves to 1, at that time this source is disconnected and we are left with this circuit. When we redraw this circuit will become like this. This is short circuit and this is the switch when it is connecting to 2 and the resistance and the inductance. Here we are having when the switch is connecting with 1. So next, now we are considering its response. Before considering its response, I want to tell you one important thing, that when we are talking about the elements at its initial position and its final position, then resistance will act same at its initial position and its final position. But when we are talking about the inductance, then it is open at its initial position. Initial position is when t is equals to 0 and final position when t is infinity. And when it reaches infinity, means final position, it is short. And capacitance, it is short circuit at initial position and open at final position. It can be remembered as IOS. I have discussed this thing in the previous lecture also. I means inductance. When it is initial condition, it is open. When it is at final condition, it is short circuit. This is C means capacitor. At initial position, it is short circuit, and at final position, it is open. So these two things are very important when we are talking about the circuits. So now we are talking the RL circuit. In RL circuit, first this circuit is shown. Now we are considering the case when switch K is connecting at the position 2, means that we are having the circuit like this. We are having this circuit, inductance L, and this is position 1 and this is key K. So we are having the voltage source, that is when the switch K is connecting at position 1, we are having the voltage source, but if we are connecting it with the position 2, then there is no voltage. In this circuit, in the first case, case 1, we are considering that this circuit means that there is no voltage source connecting to the loop because we are connecting it with the point 2. We are writing KVL across this. The KVL will become IR, the voltage drop across this resistance, plus L di by dt, because we know that voltage drop across the inductance is L di by dt. So we write it here, this equation. So this is homogeneous first order linear differential equation with constant. Apply variable separable method. When we apply the variable separable method, the equation will become di upon dt is equals to minus r upon L dt. Now apply the natural log on this condition, on this equation. It will become natural log I is equals to minus r upon L, means r upon Lt plus k. Let's consider the natural log of this k also. K is equals to natural log k. We know one formula from the mathematics, that when we are taking the natural log of c, means it is natural log of a plus natural log of b, and it can be written as c is equals to ab. So we apply this formula in our equation. Here this is the equation where we want to apply. This is natural log I is equals to natural log e raised to power r by L t plus natural log of k. So this is a and b. So we apply Li is equals to natural log k into e raised to power minus L upon t, and it can be written as I is equals to k e raised to power minus t by tau, and tau is what? This is L by R. We are replacing this value R by L with tau, and tau is equals to R by L. So this is the transient response of RL network. This is the plot of the RL response, in which we are having the transient response on this side, and we are having the here we are having the transient response, and after that we are having the steady state response. This blue line shows this equation, I is equals to V by R into 1 minus e raised to power minus R by L into t, and this purple line shows VL is equals to V upon R e raised to power minus R by L into t. And how we calculate the time constants? By putting the different values of tau. When tau is 1, we are having this equation. When tau is 2 tau, this equation, and this is how we find the values, and according to these values we plot this graph. Then next one is the transient response of RC network. As in previous I have told you that CSO means that at initial stage this capacitor is short circuit, and at final stage the capacitor considered as open circuit. Now this circuit is also divided into two circuits. The first, when initially we consider this is connecting to 2, this is the initial condition. The first case is when we connect this to 1, means 2 to 1, we are moving this 2 to 1, the circuit will become, we are having the voltage source, the resistance and the capacitor. When the voltage source is applied and switch is closed, it means that this capacitor is going to be charged. The capacitor is charged. Here we are having negative to positive, so the this plate gets positive charge and lower plate gets negative charge. So the voltage across this capacitor, when the capacitor is fully charged, this Vc is equals to Vs. Then we move this from switch 1 to switch 2, we reconnect it with this switch, the circuit will become this. When we reconnect, we left with this circuit. The voltage source is not connected in second case, so this is the case. And when the voltage source is not connecting, but this capacitor is fully charged, the voltage at that condition is Vc, the voltage across the capacitor. And when it is connecting to the switch 2, the capacitor get discharged through resistance R. So here we are doing the derivation for series RC circuit. Case 1, this is the circuit, basic circuit, in which we are having the voltage source and we are having the switches and resistance R and capacitor C. So case 1, the switch is moved to 2 from 1. Initially we consider that switch is at 2, as in the previous circuit I have cleared this. We connect it to switch 1. When we connect it to switch 1, the equation will become 1 by C 1 by C integration from minus infinity to t it dt plus ri t is equals to 0. When switch moves from 1 to 2, the equation will become 1 by C. This equation will become 1 by C integration 0 to t it dt plus v plus ri t is equals to 0. Since 1 by C integration minus infinity to 0 it dt is equals to 0, which is the initial voltage at t is equals to 0 on the capacitor, we consider this equation. This value is equals to V. Differentiating above equation, we will differentiate the equation by dividing by R. It will become di upon dt plus 1 by RC I is equals to 0. When we solve this equation, we will get this final equation. IT is equals to I infinity minus I infinity minus I0 means I initial condition, e raised to power minus t by tau, and tau is equals to RC. This is the condition for RC network. Then this is the plot for RC network. Here we compare the two cases. When we are having the RC circuit, we are having these two circuits RL. We are having these two cases. When the switch moves 2 to 1, we are having this circuit. When we connect switch 1 to 2, we are having this circuit. And these are the cases of capacitor. In the first condition, the capacitor get charged, and in the second condition, the capacitor get discharged. So based on this, we are having one numerical RC transient response. We are having one circuit in which the resistance and capacitance are connecting across a switch and a voltage source. Condition 1, initially the capacitor is uncharged, there is no charging of the capacitor, and we consider that Vc 0 minus is just before closing the switch. I have explained these conditions in the video of transient response, please check that video. And Vc plus is equals to 0 means that when the capacitor is at its initial condition, the voltage across capacitor just before connecting the switch and just after connecting the switch is 0. So current at t is equals to 0 plus at condition t is equals to 0 plus means just after closing the circuit will become this. When we closed the switch it will become this. We are connecting a complete circuit, and from here we find the value I is equals to V by R. We know the value of voltage and resistance, it is equals to 4 ampere. Now and this is the steady state condition when initially t is equals to 0. When then steady state at t is equals to infinity, the capacitor is fully charged. When we connect this battery, this capacitor gets fully charged. Look at here, we make it short circuit as we make CSO means the capacitor at initial it is 0 and capacitor at its final it's open circuit. So when we are talking about the initial condition we make it short circuit. So steady state at t is equals to infinity, the capacitor is fully charged. When capacitor is fully charged the current is 0 in the capacitor. When we consider this capacitor fully charged the current is 0. Now when the capacitor is fully charged at infinity, t is equals to infinity, we make it open circuit. This shows the open circuit, and voltage across here is Vc. We are having the two terminals across this voltage across A and B, that is Vc at infinity is equals to Va minus Vb. V is the voltage connecting from this side, it is 20, and VB is connecting from this grounding side to this, here we are having 0, so it is 0. So Vc infinity is equals to 20. And how the current is 0 in the resistance, this is shown in this figure. We are having the voltage Va 20 and voltage from here Vc is 0. I is equals to V upon R, and I write here I is equals to V upon R, but we are finding current across two terminals A and C. Then it is 20 minus Vc, Vc is 0, V, I write it here Vc upon R. When when we are having the voltage source this 20 volt, the voltage across this is the means capacitor is fully charged. Here we are having the same voltage, so 20 minus 20 upon 5 is equals to 0. So this is how the current is 0. Then at steady state Vc keeps on increasing, then it becomes I is equals to 0. This is what I have explained. Next condition second. Now this is the condition 1 when the capacitor is uncharged, and from uncharging to it gets charged. Means when we connect this circuit it gets charged, means when we make it short circuit, connect the key 2.2, it gets when we connect the key this key 2.1, this voltage source connected, and because of this capacitor get charged. Now second condition, when the capacitor is fully charged. Now because of previous condition our capacitor is fully charged. When capacitor is fully charged it is acting like a source. Source means the whatever the voltage across the capacitor is considered as the source volt. So the capacitor is charged by a Vs of 20 volts. So here we are having the 20 volts. So Vc Vc 0 minus means Vc just before is equals to 20 volt, and Vc plus 0 plus is 20 volt, because it will not release its voltage, keep its voltage same for some time. So I 0 plus is equals to Vc upon 5, and Vc is our 20, so 20 upon 5 is equals to 4. This is the capacitor is discharged by energy loss through heat. Initially it is fully charged, but with the gradual time, with the passage of time, the capacitor starts discharged with through this resistance R, and there is a power loss I square R. So C infinity, Vc infinity is equals to 0, and I infinity is equals to 0 ampere. When the current enters the capacitor, it is charged. When current leaves the capacitor, it is discharged. So here we find out the final condition, and in the condition 1 we find the initial condition. This is how we analyze the transient response of RC circuit, in which we find the initial condition of the current and the final condition of the current. Now we are considering one example to clarify the explanation of RC transient response. The circuit is given to us. This circuit, first we consider this example. The switch in the figure has in position A for a long time. At t is equals to 0, the switch moves B. Determine Vt for t greater than 0. We find out the value of Vt when t is greater than 0. So we are having the two conditions. One is this and another is this. When it is connecting to this condition is when t is less than 0, and this condition is t greater than 0. Means when switch is connecting to this point, it gives the condition t less than 0. When the switch is connecting to this, it gives the condition t greater than 0. So we can consider both the conditions. This equation, we know this is the transient condition equation for the voltage. Vt is equals to V infinity, means the final condition, plus V0 means initial condition, minus V infinity into e raised to power minus t by tau. So here we are having the three parameters to find out: V infinity, V0 and the tau value. So when we consider t is less than 0, we are considering this circuit. So the circuit will become this voltage source, resistance, and this. We are having this circuit when it is connecting here. So voltage across the circuit V0 is equals to 24 volt. This is because this is of 24 volt. So the second, when t is greater than 0, means we are considering this circuit. The circuit will become 4 ohm resistance, 30 volt, and this 4 kilo ohm. We will get this circuit 30 volt when we are connecting with this switch. So t, this is the condition when t greater than 0. So V infinity is 30 volt and R is R value is this 4 kilo ohm in the circuit. So tau is our R into C, and R is 4 and C is 3, C is 0.5. So we do the calculation here. We put these values in this equation. It will become Vt is equals to 30 plus 24 minus 30 e raised to power minus t by 2. This is 2 seconds. So we solve this by this method. We minimize the equation. This is how we solve the transient response of RC circuit. Now here we are having one more example. In this example, the same, we want to find out the voltage across when t greater than 0. We find out Vt. So for this we are again considering two conditions, when t is equals to less than 0 and t greater than 0. When t is less than 0, we are considering this circuit, and when t is greater than 0, we are considering this circuit. So we are considering one by one. We are considering first case, this condition. This circuit is redrawn here. So for t less than 0, we are having current I0 is equals to 5 upon, this is voltage source, V0 is equals to 5 plus 5, 3. This is the voltage divider rule. We want to find out the voltage drop across this 5 volt 5 ohm resistance. So the formula for this is the resistance whose value is to be found plus the total resistance into the voltage source. So we want to find the voltage across 5 ohm resistance plus the total resistance. Total resistance is this 3 plus 5 into this 24 volts. So we are having we solve this and we will get the value. Then next condition, when t greater than 0. When t greater than 0 means that we are left with this circuit and it is connecting here. We redrawn the circuit here. Now from here V infinity is equals to 30 volt and R of this circuit is 4 kilo ohm. Find the tau is equals to R into C. R value is given 4 into 10 raised to power 3 into the C value is 0.5 into 10 raised to power minus 3, because it is 0.5 millifarad. This will cut down and we will left with the value 2 seconds. Tau is 2 seconds, which we calculated here. Then put all the values into the equation. We will get Vt. We will get this Vt is equals to 30, means this infinity voltage, plus 15, which is V0, minus 30 e raised to power minus t by 2, the tau value. So when we solve it, we will get this. Now we will put the values of time. When t is equals to 1, we will get V1. When we put the value t is equals to 4, we will get another value. So this is how we solve the transient response of RC. So this is all about the transient response of RL and RC network. So before closing this video, I just want to tell you that we are having the 4 important formulas for solving the numericals, which we should keep in mind. That the first one is I is equals to I infinity into plus I0 minus I infinity into e raised to power minus t by tau. and for voltage V is equals to V infinity plus V0 minus V infinity into e raised to power minus t by tau, and tau is time constant, and it is tau is equals to R equivalent into C for capacitor, and tau is equals to R by L, sorry, it is L by R for inductance, and if more than one resistances are given, then we are find out R equivalent by finding Thevenin resistance, that is RTH. So, and these are this is first one, this is second, this is the values of tau, and another one are IC is equals to the current across the capacitor is IC upon CdV C upon dt, and the voltage across inductance is L DIL upon dt. Fine. So this is about these equations. This is third equation, fourth equation, and these are called magical equations, because with these equations we can solve all the numericals. And one more thing, always keep in mind IOS and CSO. IOS for inductance, CSO for capacitance. So this is all about your today's lecture. Hope you understand the things, and with this, thank you so much.